Welcome to our new video tutorial on to determine the frequency of alternating current using a sonometer. A sonometer is an apparatus used to study the transverse vibration of a stretched string. So stretched string means there's a two ends will be stretched and there will be a tension working inside the screen, inside the string, and string actually here in this case, that is one end is fixed, another end is free to move, but that is restricted by the mass. So we can change the mass up here, and accordingly the tension will change, and this tension formula is given by T equals to M into G. You can see this T is the tension of the string, and this T is nothing but M into G. Now when what will happen, see, let's discuss one by one. So look at the apparatus. The apparatus is made up of one main source of 220 volt AC, another is a secondary coil. That means a step down transformer is involved here, which actually reduces the voltage from 220 volt AC to a reasonable voltage what we can actually tolerate. Otherwise this 220 volt is capable of giving a high voltage shock. So what is not changing in here, for us, for this purpose, we'll only consider only one term, that is called the frequency. The frequency is not changing here, but we are getting this frequency, and the frequency here after the step down process, these two frequencies are actually same. So though it's 6 to 5 8 volts AC, the frequency is similar to that one. Now uh, this is a magnet, this N and S pole, and you can place this N pole here and S pole here, no issue. But you have to keep in mind that this string, the current carrying conductor, this string, which is also carrying a current, the direction of this current should perpendicular to the magnetic field, that is from N to S. So we are keeping this apparatus, this NS pole, in such a way, then there will be a transverse magnetic field working on the current carrying conductor. Now let's have a look on two physics. One, we will divide into two parts. One is the force acting on a current carrying conductor by a magnet. Here is the figure. You can see there's a magnetic N pole as a magnetic south pole, S pole, and this magnetic field is directing from this N pole towards the S pole, and this is a current carrying conductor. The current is flowing from this direction to this direction, and is a right hand rule along this force is acting on this direction. Now if one is one can see this voltage here is actually a DC voltage. The polarity is not changing with respect to time. If we could do that, if we change the polarity, this positive is replaced by the negative one, the negative is replaced by the positive one, what will happen? The force will be reversed. That means the force in this case, which is directing upward, now it will be directing the downwards. Now if we change this polarity periodically, or we replace this DC voltage source as by a AC voltage source, what will happen? This force will not only that keeps on changing, there will be a we can see a vibration inside this string. And what will happen if we connect these two ends with two strong support? We can see a vibration. The frequency of this vibration is same as the frequency of this oscillation, or the frequency of the AC source. Now come back to the stretched string theory. Now when the one string is stretched in between two ends, and there is a tension working as T. This T is In this case, it intrinsic T tension between the two ends, and in our case this is mg. So there should be analogy. This is mg in our case, and this T. Now this L is nothing but the length of the stretched string, and this m is nothing but mass per unit length of the wire. Now if we have these three things, we can easily find out the natural frequency of the stretched string given by this formula 1 by twice L root over of T by M. So once we get this frequency of this stretched string, we can proceed to the resonance part. So we have this natural frequency of this stretched string. Now we have the frequency of this AC, and in which frequency this is vibrating. When there is a matching in the frequency, when this vibrating frequency of the AC source, as this is the AC source is as a current value, and as we have discussed, this wire is vibrating just because of this force is changing, so there will be a vibration. And this wire is now stretched in between two ends. In this case, these are the two ends, 1 and 2. So in this case, the wire is actually vibrating, and it has a characteristic frequency, or that is called the natural frequency. When this natural frequency matches with this frequency or the AC source frequency, there will be resonance. And what will happen when there is a resonance? There will be a sudden increase in amplitude. Now let's have a look more on the stretched string. So here we have a violin. To have a brief details about how the stretched string work. So we have the G string here, and we have a E string here. This is a heavier one, and this is the lighter one. So its m value, small m value, is higher than this one. The length between this part and this part is same, you can see. Now the only difference is two. One is small m, another is the tension T. Now if we play this string and this string, this will sound something like this. You please listen carefully. So I'm just going to pluck the E string now. I'm going to pluck the G string now. Again G string, again E string. So it has two different frequencies. This is the natural frequency of the stretched string. Two different wire has two different natural frequencies. Now if you go back to the experiment, so this frequency is a natural frequency of the stretched string, and this is the frequency of the AC. Now when they matches, there will be resonance. Now let's go back to the theory. So we have a simulator here. Okay, so this is a rider. You can see rider, riding the horses, riding cycle. Now let's bring an analogy in case of the horse. So rider actually riding a horse in race course, and it's running. The horse is running that race course. Now one time will come, there is suppose a horse is jumping at this time, and that jump of the horse is tolerable for the rider. But suppose what happens, the horse jumped a lot, and that is intolerable, that is can't be tolerated by the rider. What will happen? The rider will fall down. So in that case, you have to bring that analogy with this resonance. When the resonance will occur, there will be sudden enhancement in the magnitude, and this magnitude can't be tolerated by this rider, and the rider will fall down. So we have to find out that point, at which point the rider will fall down. Now in this case, we are interested in the first resonance. We can describe this first resonance and second resonance in later videos. but let's stick with this. Now we are actually going for the Earth, that is G equals to 9.8 meter per second square. This is the Earth. So we can choose any other planets. So first of we will go for the Earth. Later on we can see in other planets value. So Earth, let it be copper, let it be AC main. So don't look at this 50 hertz. So this is the diameter of the wire, let it be 6.6. Okay, now weight of the hanger, keep it as so we can keep it at say, okay, let it be at point 0, okay, point 1, okay, keep it as point 1. Just wait, it is to 0.05. 0.05 is okay, fine. We can start from the initial value. Now position of the bridge A, we are keeping it at for example, we can keep it at 48. Now okay, the magnet is in between that, 50. Now we'll change this B value, we'll bring it closer, and we will check it whether where there is a resonance. Let it the power on, will increase, okay, we'll decrease the value. Okay, this is jumping. Now there's a vibration, you can see. Now we'll slowly go down, decrease the value. Okay, so this first resonance, we got the first resonance. So in this case we have to find out this value. So in this case this is 48.0. Position of the first bridge, that is A, is 48, and the second bridge as 62.5. We will subtract this value from the 62.5, we'll get the L value in between this. Now we have to keep it in mind. Let's power it off. This is my M value, capital M value. We have to multiply it with G to get the T. Now for the sake of simplicity, let's go back to the theory right now. So this frequency of the AC, when there is a resonance, that frequency of the AC will match with the natural frequency of the wire. So what will happen? This natural frequency of the wire should be equal to the frequency of the AC. Now we will just simply, it is a simple calculation. We are just actually separating two things. This is G by M in one part and this M by L square. Keep it in mind, this is a wrong, this step, there's a mistake. So it shouldn't be 1 by twice L, it should be 1 by 2 times root over of G by M times root over of M by L square. So when we are increasing this M value accordingly, this L will also increase or decrease. So that this frequency will remain same. So when this M is increasing, you can see this L will also be increasing, so that this M by L square value is constant. So pardon me because I previously said this for the increasing M value the L will decrease. No, so there is a change. Okay, you can see this M by L square will keep constant, and you can see that graph between the L square and the M, you will have a straight line, and if you calculate the slope, this M by L square will be a constant. Now keeping what how to calculate this value for a particular M value, you will get a particular L value. So for in this case there's 1 2 3 3 6 different masses are there. Now if we go back to the simulator, we have a different mass value. So this is 0.005, is 50 grams to 500 grams. We have 11 different steps we can do that one. So we can take 10 to 11 values, suppose 0.05, another is 1 to 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 different values, 10 different m values, and for these 10 different m values we can get 10 different l values, and accordingly we can draw this graph, and we have a different m by l square, so we will put this m and different l square, and we'll get this m by l square value. So m will be ab and this l square will be bc. So by calculating the sd, that is the smallest division in the graph paper, so we can easily find out the ab by bc. So if to calculate this ab by bc, we know the value of g, we know the value of small m. So 1 by 2, this is not 1 by twice L, this is 1 by 2. We can easily find out the value of AC. Now let's go back to the simulator again. So this is all about this. This is frequency unit. Okay, this is the AC main. Okay, so that's all for today. You can observe. If you have any queries, you can ask, and if you want to have more videos on that, on upcoming VLab or OLab session, you can subscribe our channel. Thank you.